question as old as humanity itself. Are we alone? Is Earth the only refuge in the entire universe for this complex, fragile, and yet somehow prolific and enduring chemical reaction that we call life? Now, the space race of the 1950s and 60s paid many dividends to humanity. Most of them were practical in nature. Materials that we often take for granted today, like the mylar used in balloons and emergency thermal blankets, memory foam used in modern mattresses, certain CCD camera technology, and scratch-resistant plastic lenses all find their nascence in the laboratories of NASA scientists and engineers. These practical solutions offered as a byproduct of space exploration are an undeniable benefit to the expenditure of effort and financial resources in the quest to understand our solar system. But what about the more direct questions that NASA organizations strive to answer? And questions like, can we establish self-sustaining colonies elsewhere in the cosmos? Or might there already be life thriving in undiscovered regions of space? These are some of the fundamental questions of our generation. And as we creep ever closer to the very real possibility of colonizing our solar system someday, and the still sometimes hopelessly daunting task of reaching points beyond, it's more critical than ever that we understand how it all works at a chemical level. So let's spend some time exploring the universe beyond our tiny little protective sphere called Earth, considering what it's made of and how we might survey it for conditions favorable for human life, and maybe even find life already waiting for us to make contact. Let's prepare for our journey by first thinking about life as a chemical process. Now, as we understand it, life requires a few specific conditions to evolve and thrive. We've already learned what a remarkable compound water is. Its high polarity, powerful hydrogen bonding capability, and composition of hydrogen and oxygen, two of the most abundant elements in the universe, all make it a must-have for life as we know it to evolve or survive. Carbon, of course, we talk about carbon-based life when we discuss the chemistry of living systems. Now, largely because only carbon seems to have the right combination of bond stability, complexity, and overall availability to serve as a backbone for the molecules of life. So simple organic molecules will also be part of our search. Detecting the presence of water and organic molecules in deep space might sound like a real challenge. And make no mistake, it is. But the techniques used to search for these substances are some of the oldest and most well-developed techniques known to chemists. We need only find ways to apply them when the object under study is millions of miles away, or even light years away. Pretty significant wrinkle, but it's not insurmountable. Our search can exploit many phenomena that we've discussed so far in our investigations of chemistry here on Earth. Spectrometers will be pointed into deep space to look for infrared light, which can tell us about the kinds of bond vibrations taking place in the atmospheres and on the surfaces of stars, planets, and moons. We'll use the mass spectrometers inspired by J.J. Thomson to literally weigh the molecules swirling in the atmospheres of gas giants as these instruments plunge into their deep, murky atmospheres. At times, X-ray diffraction can be used to determine the structures of minerals on rocky surfaces, giving us a window into the conditions on planets long ago when those minerals formed. In short, we're going to bring most, if not all, of our chemistry expertise to bear on this question and try to answer the question, what is the nature of life in our universe? Are we a cosmic accident, doomed to flicker out of existence on a single, small planet in the corner of the Milky Way? Or is life an integral and distributed part of the fabric of the cosmos? Can humanity reach the stars, and has life itself already beaten us to it? It should be a remarkable journey. We're well prepared, and our time to take it is limited, so let's get started. How far has water come in the minds of men and women in the last few centuries? I mean, we've always known that it was essential to life. But in recent years, as the complexity of life's biochemistry has come to light, the importance of water has really started to sink into the human perception. Water is such a simple molecule, two of the most abundant and simple elements in all the universe. But put them together in the right way, and you have a compound that, so far as we know it, is indispensable to life. from the bacteria that live in glacial ice that we call psychrophiles or cryophiles, to those that live on the ocean floor vents at hundreds of degrees Fahrenheit called thermophiles. From highly radiation-resistant organisms like radiodurans to acidophilus, which is capable of living in pH values lower than the historically low values measured in West Virginia in 1970. All of these remarkable adaptations have still required at least one critical compound to exist: water. So our search for life and environments that can sustain it starts with water. So we'll be looking for water out there. But how? How do we detect water on the moon? On other planets? Even in deep space? The answer is we do it very much the same way that we would right here on Earth. Now that became a real possibility with the achievement of the Apollo missions. Manned missions to the moon gave researchers a very real chance to place instrumentation directly on the surface to look for signs of this critical substance. The final few Apollo missions to the moon were a much-needed success after the Apollo 13 disaster. The brave astronauts who participated in those missions accomplished a lot. They took a few photos, Alan Shepard hit a few golf balls, and they got to play with a really cool dune buggy. Oh yes, and they placed an array of instrumentation on the surface to investigate exactly what the moon was made of, sending invaluable information about the chemistry of our nearest cosmological neighbor back to us. Among those instruments was a mass spectrometer, not all that different from those developed by J.J. Thomson. This experiment, called the Superthermal Ion Detection Experiment, or SIDE, apparently everything NASA does has to have an acronym, was left on the surface by the crew of Apollo 14 when they departed from the moon on February 7, 1971. 1 month later, scientists monitoring the device were astonished to find a few distinct puffs of a vapor with a mass of 18 atomic mass units. What was it? Was it a sign that water could exist on the surface of the moon? Well, unfortunately, no. This was a real gotcha moment in the search for life in the cosmos, as 4 more years of attempts to find water with the mass spectrometer were fruitless. And the coincidence of the original measurement with the first lunar sunrise since the mission made it fairly clear that this was moisture carried in on the instruments, vaporizing under the intense rays of the sun as they were exposed for the first time. Now, this little anecdote underscores a tricky issue with the idea of sending probes to a location in the solar system in an attempt to detect life or its essential components. It's always possible for those substances to hitch a ride along. So it would be nice if there were a way that we could prospect for water without having to send a manned mission and leave behind equipment in a fixed location. Here it is. The vibration of chemical bonds gives them the ability to absorb infrared light, but only very specific frequencies that depend on the types of atoms involved in that bond. Now, water itself does this with great efficiency. So much so that it's a property we can use to look for water in the atmospheres of planets, simply by assessing how well they absorb certain infrared light. The Spitzer Space Telescope, for example, is now in its 2nd decade of service. And the Spitzer has been used to survey so-called exoplanets, or those planets outside of our own solar system, for traces of atmospheric gases like water, which might point to planets capable of supporting human life, or possibly harboring life all their own. The key feature, the first thing that we look for to weigh the odds of water existing on a distant region of space, is an absorption band at 3 micrometers. This falls into the infrared region of the spectrum, hiding from human eyes, but detectable by the electronics in the Spitzer instrumentation. Now, when light of this frequency is absorbed, it's usually by an OH bond. And what's a sample of water if not a huge collection of OH bonds? Let's take a look at how this might work. Imagine a star, much like our own sun, but this star is many light years away. Now, stars like this one are going to emit an array of radiation as a result of the powerful fusion reactions going on inside of them. And some of that radiation is going to be infrared light. Now, imagine looking at that star through the Spitzer Space Telescope, which can see that infrared light coming from the star. If a planet happens to pass by out there, And that planet that's trapped by that star's gravity happens to have water vapor in its atmosphere. Just an ever so slight amount of the infrared solar radiation will be absorbed as the planet passes by. Now, that decrease in the specific wavelength of light absorbed by the OH bonds should result. And since all light moves at the same constant speed through space, that light propagates across the vacuum of space, with that slight reduction in the 3 micrometer wavelength light moving right along with it, ready to be detected by anyone watching at the moment it passes by. NASA scientists used this technique in 2014 to confirm that a newly discovered exoplanet, HAT P11b, has water vapor in its atmosphere. This particular planet, it's about the size of Neptune. It's 120 light years away. Now, even from that distance, it sends clues to its composition to us in the form of light that has interacted with the matter in its atmosphere. 120 years after a small amount of infrared light was absorbed by water molecules in HAT P11b's atmosphere, the remaining light from its star reached Spitzer and divulged this important detail about the presence of OH bonds from water molecules in an atmosphere as it passed through more than a century ago. There is still a great deal of debate over just how life got started here on Earth. And we can say a few things with relative certainty. For example, there must have been liquid oceans, which means that not only was water present, but that the surface temperatures of the planet were moderate enough to maintain liquid bodies of water. And of course, another must-have to produce the incredible chemical reaction that is life is carbon-based compounds. And this is where things get a little tricky. In a living organism, biomolecules like DNA must be self-replicating, meaning that one strand can create another. But there's a circular process going on in living systems. DNA is translated into RNA, which is used in the production of proteins. But those proteins assist in DNA management by performing tasks like repairing mutations and helping the DNA to wind itself up properly. So you can't make proteins without RNA, you can't make RNA without DNA, and you can't make copies of DNA without proteins. It's the classic chicken or the egg conundrum. Which came first? The answer is, we simply don't know. But there are some related questions that we can ask. For example, if amino acids and proteins were the original biomolecule, how could they form without the aid of a living system? This question was put to the test by Stanley Miller in 1953, when he created a simulated early Earth atmosphere in his laboratory and was able to produce amino acids inside of it using only non-biological materials: water, methane, ammonia, and nitrogen. But Miller's experiment isn't the only possible explanation of how life began on Earth. There are others who believe that it did not begin in an electrical storm on Earth 4 billion years ago, but rather that the materials necessary to spark life may have fallen from deep space itself. In 1969, a meteorite smashed into Victoria, Australia. Observed by many, there was no arguing this rock fell from space. A recovery effort collected more than 100 kilograms of material from this meteorite, with some pieces being as large as a kilogram. But it isn't the meteor impact that's truly noteworthy here. After all, the Earth is under constant bombardment by meteors from outer space. What is remarkable about the Murchison meteorite is not that it hit Earth, but what it brought along for the ride. Researchers at NASA's Ames Research Center tested freshly broken pieces of the meteorite, looking for any signs of molecules that might provide a seed for life. And they were not disappointed. By extracting the contents of newly exposed surface of the meteorite, then isolating the organic components using a separation technique known as chromatography, the researchers at Ames determined that there were no fewer than 7 different amino acid compounds trapped within the matrix of the Murchison when it fell to Earth. Over the past few decades, as analytical technologies have continued to improve, the meteorite has been occasionally revisited and analyzed again. As of today, more than 50,000 distinct carbon-based chemical compounds have been identified within. including not only amino acids, but the purine and pyrimidine bases essential to the construction of DNA as well. All of the organic molecules coming from the Murchison existed as equal mixtures of left and right-handed compounds. But many of these organic molecules in us are only of one-handedness. For example, our amino acids are practically all of the L-handedness. Now, furthermore, mass spectrometers show that their isotopic composition was not consistent with biological sources like our seafloor methane hydrates that we discussed previously. So these tests are an indication that they were not likely created by a living system. This is a bit disappointing at first, as a different result might have proven the existence of extraterrestrial life. But it does make an interesting and exciting point. If these compounds can form in lifeless rocks in deep space, and if they can fall to terrestrial planets and seed them with the materials needed for life, then this could happen just about anywhere in the cosmos. This idea was actually offered much earlier than the Murchison impact. In 1908, Svante Arrhenius himself postulated that the materials needed for life might fall from the stars in a process that he called panspermia. A process like this might very well explain how life was able to gain a foothold so quickly on the surface of the early Earth, and the Murchison meteorite would seem to lend some gravity to this theory. But this opens up an even more challenging question. If the Murchison carried with it a library of tens of thousands of different organic molecules, and those molecules strongly appear to be non-biological in origin, then just how did they get there? How can organic compounds like amino acids and purine or pyrimidine bases form in deep space? It seems somehow impossible that atoms and simple molecules could collide in the vacuum of deep space to create something so complex. Well, the answer, in an interesting twist, turns out to be ice. That's right. The most promising theory involves interstellar grains of ice acting as minuscule chemical reaction vessels. We have the Spitzer telescope to thank for this theory. See, when NASA scientists pointed it into deep space for a look in the infrared, they saw something very intriguing. When staring into deep space measuring a faint infrared radiation that permeates our universe, occasionally clouds of interstellar material will drift into the telescope's field of view. When this happens, a fairly strong infrared absorbance is measured at, you guessed it, about 3 micrometer wavelengths. This corresponds to the vibration of OH bonds in ice in deep space. And if that isn't remarkable enough, the rest of the spectra of these features showed evidence of small molecules like carbon monoxide and carbon dioxide, as well as methanol and methane. There's even evidence of larger hydrocarbon compounds called polyaromatic hydrocarbons. And if all that weren't enough, there are still many infrared absorbances from deep space that are yet to be identified, but very likely the results of additional organic compounds trapped within those small grains of interstellar ice. So how do we explain the spectral conformation of interstellar ice and organics? Well, the leading theory is this. Small grains of ice contain even smaller pores within them, giving them a very large surface area for their size. Because of this large surface area, interstellar atoms, small molecules, and polyaromatic hydrocarbons are preferentially adsorbed to the surface, along with one another. So the ice grains act like an interstellar sponge, sopping up interstellar atoms as they're encountered. This process concentrates all of these compounds in contact with the ice, allowing them to react with one another. Add a bit of energy from radiation, and you have everything you need to run a sand grain-sized chemistry laboratory in deep space. Now from there, it's not much of a stretch to imagine some of these grains finding their way into a forming solar system, seeding it with the compounds needed to create that spark of life. It's humbling to think that the first living systems might have contained at least a few molecules that were forged in deep space before falling to Earth. And if that scenario is indeed the case, our exploration and eventual colonization of space might be viewed more as a homecoming than a migration. In any case, these findings reinforce the common belief that if we do find life elsewhere in the universe, it is highly likely to have a chemistry very similar to our own. In the spirit of that last comment, let's turn our attention from where we came from to where we're going. In addition to understanding how life comes to be on planets, another driver for space exploration is the desire to find new outposts for human civilization. New celestial bodies to call home would mean more space for our growing population, and one would assume more natural resources to be harvested as well. But as Venus and Mars teach us, creating the perfect balance of tectonics, atmospheric composition, and a temperature conducive to the presence of liquid water can be a very tricky balancing act. With billions upon billions of terrestrial planets likely in our galaxy alone, it is highly likely that there are some that meet the necessary criteria. It's always nice to find your next home move-in ready, right? But there must be something we can do to hedge those bets. To carry on our analogy of house hunting, what about the fixer-uppers? Is there anything we can do to improve the inhabitability of planets that show promise but aren't quite perfect? Well, in theory, there is, and it's a process commonly called terraforming. The concept was first popularized by H.G. Wells in his 1898 classic War of the Worlds. In Wells' story, alien invaders bring with them to Earth a plant native to their own planet. Now, this concept of changing a planet's atmospheric chemistry using plants was revisited in many science fiction novels throughout the early 1900s, though the topic was often the conversation of an alien world to suit our needs as opposed to Wells' version of exactly the opposite. American science fiction author Jack Williamson first coined the term terraforming in the 1940s. And this somewhat romantic idea that new worlds could not only be explored but created caught on. So much so that by the 1960s, great astronomers like the incomparable Carl Sagan were beginning to bring their expertise to bear on this concept. Sagan famously outlined a plan for the terraforming of Venus in a 1961 issue of the highly renowned scientific journal, Science. Sagan revisited this idea a second time in 1973 when he published his thoughts on altering the chemistry of our other close neighbor in the solar system, Mars. These two planets could not be any more different when it comes to their atmospheres. Venus with a crushing, acidic, runaway greenhouse, and Mars with its cold, thin, all but stripped away atmosphere. In both cases, it seems that the key to bringing their environments under control is to manage the greenhouse gas content of their atmospheres. So how might we do that? Sagan suggested spreading a dark material across the poles of Mars to warm them by absorbing solar radiation. This would release the carbon dioxide gas trapped there as a solid. Now, his hopes were that the release of this greenhouse gas would warm the planet somewhat, prompting the release of even more carbon dioxide in a controlled buildup of CO2 and therefore planetary heat. More modern plans have been advanced to accomplish the same feat that Sagan suggested was possible in 1973. One suggestion involves the use of refrigerants, of all things fluorinated hydrocarbon gases, which have replaced ozone-depleting CFCs in many refrigeration units on Earth. They might act as a sort of jump starter for global warming on Mars. These compounds absorb infrared radiation in spades. And the high-polarity carbon-fluorine bonds are practically custom-made to absorb infrared radiation, which are emitted from the surface of the planet as it warms under the influence of the sun. Again, these gases promote heating of the planet's atmosphere. More and more carbon dioxide should sublime from the poles, eventually taking over and dominating the chemistry of the Martian atmosphere. Even more recent advances in bioengineering are again changing the way we think about our ability to alter climates. We've long known about cyanobacteria and the role that they played in altering the atmosphere of our own early Earth. They're remarkably resilient bacteria, requiring little more than liquid water, light, and time to thrive in all but the otherwise harshest of environments. And as researchers determine new ways to make them even more robust, it seems that someday we may find ourselves deliberately seeding the red planet with cyanobacteria. This would be done in the hopes that they will again do for Mars what they did for Earth, consuming a portion of the newly liberated carbon dioxide in photosynthesis to create a steady source of not just an atmosphere, but one with oxygen contained inside. And finally, in a stunning development, NASA recently announced, this was in October 2015, that its Mars rover had photographed what appears to be a briny solution creeping down the walls of several craters on Mars. Infrared studies have confirmed recently that those areas around those streaky formations contain high levels of hydrated minerals. And that means that water is somehow associated with their formation. It may yet be a bit early to start celebrating, as follow-up studies will have to be conducted to confirm the findings. But it kindles the imagination to think that water may actually be present on Mars today. If that's true, there may be life. And if that's true, terraforming Mars may be much easier than we ever thought it would be. If life is clinging to the red planet somehow in relation to those features, there exists a chance that all it needs is the appropriate nudge to reclaim the rest of its world and establish the chemical balance that we enjoy here on Earth every day. Who knows? The lessons that we might learn from such a project could even one day help us to take a hand in undoing some of humanity's impacts on our own global chemistry, altering the chemistry of our home planet for the better. Encapsulating all of the remarkable chemistry that takes place on other worlds and in deep space in a single discussion is nothing short of impossible. But we've made a really good start. We investigated some of the ways that researchers look for water in our solar system, particularly by scanning the heavens for that signature infrared absorption at 3 micrometers caused by water's life-sustaining OH bonds. In doing so, we talked about how orbiting science instruments like the Spitzer Space Telescope are used to detect the presence of molecules like water, not just on other planets, but in deep space itself. Then we took some time to consider the concept of panspermia, Arrhenius' proposed idea that the original molecules of life fell to Earth from the heavens. We saw how the Murchison meteorite fell to Earth in 1969. Bringing with it a payload of tens of thousands of different organic compounds, leading scientists to believe that maybe Arrhenius had it right. Then we pointed Spitzer at deep space and used its infrared sensing eyes to find not only ice particles out there, but organic material as well. And we discussed how it very well may be that the first amino acids or DNA bases on the surface of the Earth actually formed on an ice crystal in deep space. Finally, we took a break from observing the chemistry going on outside our own atmosphere and started to think about doing some chemistry of our own, as we discussed the concept of terraforming. We thought about how Venus presents a significant challenge to this kind of project, so significant that Venus is seldom mentioned in discussions of terraforming anymore. But then we turned our attention to Mars, and we saw how there is a tremendous amount of evidence that Mars can be, and actually once was, a thriving planet with liquid water. Then we took a look at a few plans that had been offered over the years as a means of warming the red planet back to usable temperatures. From Sagan's plan to change how Mars absorbs solar radiation, to the use of super greenhouse gases, to using a microbial army to produce the atmosphere that we desire, we saw how the more we learn about Mars, the more possible this kind of project seems to be. I hope that these 60 lectures were informative for you. I hope that you got some answers to questions that you might have had about matter and its properties. But more than that, I hope that they left you with all new questions and a desire to apply the knowledge that you've gained in pursuit of their answers. 60,000 lectures aren't enough to exhaustively cover all of the amazing chemistry going on in and around us. And I hope that you think of this moment as much as the beginning of your own personal journey on the study of chemistry, and less like the end of ours together. Nonetheless, the time has come for us to part ways. But I do so in the knowledge that you now have all the tools that you need to participate in detailed discussions on how the matter that makes up our universe works at the atomic and molecular scale. I encourage you to do so. Take the basic material that we've covered in this course and use it to build your very own personal understanding of all things made of matter. From subatomic particles to the deepest reaches of space, our journey is complete, and I thank you for your attention.